Hi everyone, Rimple Sandhu here. I'm a postdoc at National Wind Technology Center. I'll be talking about some technical details behind our stochastic Soaring Raptor Simulator that we're calling SSRS. That's the tool that we'll be testing later on in the interactive session. So problem statement, we want to model golden eagle behavior. We want to model their movements at turbine scale resolution so that we can compute the presence and the risk near the turbines. We need to understand this because golden eagles are protected species and they are obligate soaring birds. So there is wind turbines and golden eagles are trying to use the same wind resource. So that's why there's a conflict. And on the bottom left, you see a picture of actual golden eagles traveling very close to wind turbines. So we want to be able to predict movements such as these so that we can then design ways to mitigate the risk to golden eagles from turbine collisions. So the goal of this work was to construct a predictive movement model that if you give it a starting location of a golden eagle and current wind conditions, it will be able to simulate the path of an individual eagle. We want the model to be predictive. So we want to be able to predict conditions that we may not have seen before. It's agent-based. That means it simulates the movement of each eagle individually. It treats each eagle as an entity, independent entity. It's probabilistic. We want to incorporate the uncertainties that are involved in atmospheric conditions, eagles' decision-making, where it's located, where it's entering the region. We want it to be generalizable. We want the model to be used at any site across the US and other regions. Microscale, we want to be able to simulate movements at turbine scale resolution. So we're talking about 20 meters, 30 meters, 50 meter resolution. It has to be validated. We have to check the model against telemetry data to see if it actually gives some realistic movements of an eagle. And we can use this the most important one for this work was orographic updraft, because when they're using orographic updrafts, their altitude is closer to the rotor swept zone. When they're using thermals, they're probably higher, that there might not be as much risk as when they're using orographic updrafts. So we started with focusing on orographic updrafts and the thermal updrafts only, and the season and time of the day. Future work will tackle other factors here that may affect golden eagle behavior. So we designed this tool, Stochastic Soaring Raptor Simulator. It's a tool that's available for anyone to use, and we'll be testing this out in the interactive session. So let me talk about some of the mathematical details of this tool. So there are three entities. There's atmosphere, the land surface, and the golden eagles. And once we know the atmosphere and the land surface, that goes into the updraft model that we just talked about in the previous talk. So we can estimate the orographic updraft, the thermal updrafts. That goes into a movement model where you tell it, okay, this is where the golden eagle is. This is the updrafts simulated traveling in some general direction. Once we have the movement model, we can then validate the model or make probabilistic predictions. So we're using publicly available data sources, and that's why this tool, that was one of the priority for designing this tool, is we want to make sure that anyone can use it for any region. So we're using NREL's wind toolkit that Carolina talked about earlier, NOAA's HER data set, and we are extracting terrain from NASA's SRTM, which is a 30 meter, and USGS 3D EP product that has 10 meter resolution in the US. So that's quite a high resolution terrain altitude, slope, and aspect information that we can use for our model. So the model, the tool actually goes out and extract these data sets itself. And then we can extract wind turbine locations from USGS database that's updated monthly. So if there's new turbines that come up, this tool will automatically pick it up and show you when you run the code. So the updraft models, I'm not going to go into detail. We just already talked about. So once we have terrain information and the wind conditions, we can estimate that the orographic updrafts and the thermal updrafts. We're going to be updating these models based on what we just mentioned earlier. So we'll have better models of estimating the updraft fields. But the idea here is you extract wind conditions, wind speed, wind direction, temperature, pressure, boundary layer height, and then you can estimate these updrafts. The movement model is based on a fluid flow principle. So the idea is that golden eagles, if they want to travel from point A to point B, they want to minimize their energy expenditure. They don't want to use too much energy. So that's the idea. This differential equation is basically, it's used in, it's also known as Darcy's law. But the idea is minimizing the energy of each golden eagle for traveling from point A to point B while using only one resource, which is the updrafts. And so we developed this stochastic movement model where we not only consider that golden eagles will always make the best decision for themselves, so we are introducing some stochasticity and some variability in eagles' decision making. So we are allowing it to make some missteps while it's traveling. So you'll see here that at each move, we give it a golden eagle sees a list of probabilities in each direction, and it chooses based on where to move based on those probabilities. And there are some parameters that we can play around with to change those stochasticity levels. So we started with applying it to a region in a wind site in Wyoming called Top of the World Wind Power Plant. This site, we chose it because there has been documented evidence of golden eagle fatalities at this site and the sites close to this. And we have golden eagle telemetry data available and fatality data available for this site. So this is a perfect site to test this model on. So you can see here, it's in Wyoming. We chose a 50 kilometer by 50 kilometer region at 50 meter resolution. And there are 3 wind power plants there. Major ones, Top of the World, that's in black. That's an actual picture of the Top of the World power plant. There's Rolling Hills and there's Campbell Hill. So this is on the right, I'm showing the telemetry data that we have for this 50 by 50 kilometer region, but I'm only showing data. So these are tagged golden eagle birds that are traveling, that are moving, and their movements are captured by the GPS unit. And I'm only showing the low altitude flight. And one thing we can notice here, this red and orange regions are always in the western or southwestern side of the ridges. And when we look at the wind rows for that side, we can see the winds are mostly westerly or southwesterly. So piecing these two things together, we can say they're probably using orographic updrafts. That's why they're always, when they're at low altitude flight, they're on the western or southwestern side of the ridges. So this is interesting because then this model will be ideal because it can simulate movements based on orographic updrafts. So SSRS workflow, how does it work? So we start with the topography and the atmosphere. So we have the terrain elevation, the slope, the wind speed, and wind direction. We compute the orographic updraft field from that. Then we simulate the eagle tracks. So let's say I'm saying the golden eagle has been spotted on the southern boundary at the middle of this domain, and it's trying to go north. Which way, what does the model say? So these are 500 golden eagles, simulated golden eagle tracks, trying to travel north, starting from one point. And you can see here that most of them are trying to go via Campbell Hill power plant and not the other way, the other power plants. So from that, we can compute the relative presence density. So what that is it tells you where a golden eagle is likely to be present compared to other sites in this region. It doesn't give you the absolute presence, it's the relative presence. So it will tell you, okay, this site is more likely to have more golden eagles than the other site. Once we have this, since we're running at 50 meter resolution, we can go to turbine scale presence. So now we can say which turbines for a particular power plant are gonna be more likely in the routes of golden eagles traveling in this direction. And from that, we can feed that information to the turbine control or plant siting so that we can take appropriate measures. And if you have avian detection systems like identified flight systems, you can then feed that information back to the SSRS to update the location of the golden eagle and the wind conditions. So we want to validate it. So we chose 4 tracks from the telemetry data that we thought was using orographic updrafts, and then we simulate the tracks from the SSRS, and we compared the two, and we designed the likelihood ratio, a measure, a quantitative parameter that will tell you how good your model is compared to the real track. And we noticed that our model performed really well, except when the altitude above ground level of the observed tracks was higher. So that makes us think that this model is reasonable when you're trying to predict a low altitude orographic soaring flight. But if the bird is at higher altitudes, it may not predict as much reasonable as it can. But then our entire goal is to simulate low altitude flights. So when the bird is very high above the rotoswept zone, it's probably not at risk anyways. So we think this is a reasonable model for predicting those low altitude orographic soaring flights. And then we can use this model to predict seasonal presence. So here I'm showing southerly migration in fall, northerly migration in spring. You can see in southerly migration, there's more presence at top of the world than it's in northerly migrations. So this is interesting that we got this, that shows the contrast between 2 migrations. All the details are in this paper that got published recently. It's out there. Go check it out. It has all the additional mathematical details regarding this model.